Hi everyone, I hope you're okay. This is video number 6, guys, which simply means I'm doing question 6 from the November 2023 Physical Science paper 2. If this is the first video you come across, just know that there are 5 videos before this one and there will be 3 videos after this one. You can just download the question paper, answer the questions with me. If there are things you're not sure about, please do write on the comment section. I'll definitely come back to you. And don't forget to subscribe, guys. Don't forget to subscribe. Okay, question 6. Consider the following hypothetical reaction reaching equilibrium in a 4 cubic decimeter container, closed container at 150 degrees Celsius. Okay, we have our chemical reaction there. Okay, the graph below shows the change in amounts of reactants and products over time. Okay, write down the meaning of reversible reaction. A reversible reaction is a reaction whereby the products can be converted back into reactants. Right, together. So 6.2, they want us to state Le Chatelier's principle. Le Chatelier's principle states that in an isolated system, when chemical equilibrium is disturbed, the system will shift in such a way that it will favor the reaction that will cancel or oppose the disturbance that was made. That's Le Chatelier's principle. Yeah? Okay, then 6.3.1. A change was made to the equilibrium mixture at 80 seconds. Okay, there's the change they're talking about. Write down the change at 80 seconds that happened. Okay, the bold graph here represents A2, né? And A2 is our product. So what has happened here was that they have increased the quantity of A2. In this case, since on the y-axis we have number of moles, that means they've increased the number of moles, right? But remember that number of moles is not a factor that can affect a chemical equilibrium. However, if you increase the number of moles, you will increase the concentration. Why? Because the number of moles is directly proportional to your concentration. Once you increase here, you are increasing this case. So the change that was made there, you'll simply say there was an increase in concentration of the product to A2. Are we together? And then now we are supposed to use Le Chatelier's principle to explain how the system reacts to this change. Remember that Le Chatelier says the system will try to cancel or oppose the change that has happened. Are we together? How so? By favoring the reaction that will oppose the change. So what has happened here was that they have increased the concentration of A2, which was the product, right? So for us to oppose the change, opposing the change, that means we want to decrease A2. Are you together? If we decrease, the only way to decrease A2 is if we favor the reverse reaction. Are you together? And whenever the reverse reaction is favored, remember that not only A2 will decrease, but also B2 will also decrease, because we need both A2 and B2 to form AB. If these two increase, this one will later increase. Are you together? So this is how the system will try to oppose the change. As you can see here on the graph, the change that happened, the system tried to decrease A2. Are you together? It has decreased. It's from 10 moles to 8 moles. That means it has decreased the number of moles, right? Same thing happens to B2, which is the product. B2 moved from 4 moles to 2 moles. Are you together? However, the reactants have increased. They moved from 6 moles to 10 moles. Are you together? So the change that happened, an increase in the concentration of A2 will force the system to favor the reverse reaction. And whenever the reverse reaction is favored, both the quantity of A2 and B2 will decrease, and the one of 2AB, or rather of AB, will increase. Are we together? So that's how that's how the change was going to be cancelled there, or opposed. Okay, 6.4, they want us to calculate the equilibrium constant at 120 degrees. Equilibrium constant at 120 degrees. Remember that our Kc value is equal to the concentration of products over the concentration of reactants, right? So simply have A2, the concentration of A2 multiplied by the concentration of B2 divided by the concentration of my products, AB, raised to the stoichiometric coefficient. Okay, remember that concentration is always number of moles over volume. We do have the number of moles of both the products and reactants at equilibrium. All right, together. So 120 degrees is here. I do have the number of moles of my reactants, number of moles of both my products. Né? So my products for A2, I have 8 moles, divide by 4 to find my concentration, and then I have 2 divide by 4 all over. For my products, I have 10 divide by 4 all squared. Remember that the volume is 4 cubic decimeters, right? So now I just need to calculate the concentration. I have 8 over 4 multiplied by 2 over 4 all divided by 10 over 4 squared. This will give me 0.16 as my Kc value. That's 0.16. Okay. Kc is equal to 0.16. Okay, at 120 degrees, the temperature of the system is decreased to 100. Okay, firstly, the temperature was 150, a positive 150 degrees, right? Which simply means that whenever you decrease the temperature, guys, the first thing they want us to do is to draw the potential energy diagram. Okay, what kind of a reaction is this one? Is it endothermic or exothermic? Let's check what happens whenever temperature is decreased. Okay, we are told that at 130 T130 here, temperature is being decreased, right? Whenever we decreased the temperature, we ended up decreasing our products but increasing our reactant. Together we can see that our products have decreased here, but the reactant have increased. Together. So what has happened was that this type of a reaction was an endothermic reaction. Why am I saying that? Because always the time whenever you decrease your products, you disadvantage your endothermic reaction. Yeah? So in this case, it simply means that our heat of reactants was on the right hand side. Are you together? So whenever you decrease on this side, the system will try by all means to counteract the change. Are you together? By making sure that it tries to increase the temperature. How so? By favoring the reverse reaction. Whenever they favor the reverse reaction, they will decrease here, decrease there, but this will increase. Are you together? If the forward reaction was exothermic, it was going to be opposite. The heat was going to be on the right hand side, the heat of the reaction. Are you together? So in this case, I can conclude that this reaction was endothermic. Why? Because a decrease in temperature has decreased my product, but has increased my reactants. Remember that, guys, whenever you decrease temperature, you always favor your exothermic reaction. So this thing simply means that the reverse reaction is the one which was favored. Hence I say it is exothermic, and the forward one is endothermic. Are you together? And the potential, where will I draw it? Let me draw it here underneath. The potential energy diagram for endothermic reaction to be like this. To be like that now. Okay. Please note that for endothermic reaction, our enthalpy is greater than 0. So the heat of the product has to be greater than the heat of the reactants. That's why my graph is like that. Are you together? And then now we are being asked, will the equilibrium constant at 100 degrees be greater than, less than, or equal to? The equilibrium will be less than. We can all see that the reactants have decreased, but the products have increased. If you decrease the reactants, you are decreasing the numerator, you are making the number even more smaller. Are you together? But it's fine. If ever, guys, your forward reaction is endothermic, whenever you decrease your Kc, whenever you decrease your temperature, rather, you will always decrease the Kc value. Are you together? Why am I saying that? Because if you decrease a temperature in an endothermic reaction, the products will be smaller than the reactants. Are you together? However, if you increase temperature in an endothermic reaction, you will always increase your Kc value. Why? Because you will increase on the product and decrease on the reactants. Are you together? That is applicable if and only if your forward reaction is endothermic. Let me repeat. On an endothermic reaction, if you decrease your temperature, you will always decrease the Kc value. Why am I saying that? Because whenever you decrease your temperature, you will always favor the exothermic reaction. In this case, the exothermic reaction is the reverse reaction. Whenever the reverse reaction is favored, you are decreasing on the products and increasing on the reactants. That's why the Kc value will decrease. Are you together? In the same in the same endothermic reaction, let's say now the temperature was increased. If you increase the temperature, you will always favor the endothermic reaction. And if you favor the endothermic reaction, the products will increase and the reactants will decrease, and hence the Kc value will increase. Are you together? So in this case, they've decreased the temperature in an endothermic reaction, therefore the Kc will decrease. Okay, the initial reactants, or the initial reaction now takes place in the presence of a catalyst at 150 degrees. Describe the change that will be observed on the graphs between time 0 and time 60. Okay, firstly, what will happen here, remember that, guys, a catalyst always speeds up the reaction, yeah? But in this case, we have reversible reactions. We have a reversible reaction. So if you add a catalyst in a reversible reaction, we will increase both the forward and we will increase the rates of both the forward and the reverse reaction. Are you together? So what will happen here? Rather, the graphs will be more steeper. Will be more steeper. However, they will still reach the same values at equilibrium. Let's say this one will be like this, and then these two will be like this. Are you together? So the graphs will be more steeper because the rates of reaction is increased for both the forward and the reverse reaction. However, catalyst does not tamper with the equilibrium constant, so the reaction will still reach the same equilibrium, the same quantities at equilibrium together. So the only change that would be there is that the graph will be just the graphs will be steeper. Whew, I really hope that, guys, the videos helped you. Just stay tuned and wait for more. Thank you.